Hello, I'm Kathryn Goodenough from the British Geological Survey, and I'm going to talk to you about some of the work that we've been doing over the last 10 years or so on the geology and resources of the rare earth elements, with a focus on Europe and Africa. And whilst my name is on the slide, I really should say that this is the work of some much bigger teams. I've been involved in some major projects over the last few years, the EU Rare, SOS Rare and High-Tech Outcard projects. And any work that I talk about here is very much produced by the teams involved in those projects. So the rare earth elements, what are they and why do we care? Well, the rare earth elements, of course, are a group of elements. They include the 15 lanthanides, plus usually scandium and yttrium. And they're divided into the light rare earths and the heavy rare earths. There's a bit of discussion about exactly where that boundary lies, but it's generally agreed that lanthanum, cerium, praseodymium and neodymium are definitely light rare earths. And they have a really wide range of uses in modern technologies: phosphors, catalysts, glass, ceramics and polishing, but most importantly, they're strongly paramagnetic and they are used in high-strength magnets that are important for motors in such things as wind turbines and electric vehicles. So rare earth elements really are going to be critical to the energy transition. But not all rare earths are equal. We talk about the most critical rare earths, and those are in particular the ones that are needed for magnets: neodymium, dysprosium and praseodymium. And if we look at this forecast diagram from Roskill data, what we can see is that some of the technologies are expected to remain fairly stable in terms of demand over the coming years. And that means demand for some rare earths will also remain stable. But demand for magnets is expected to steadily grow. And with it, demand for those magnet rare earths, such as neodymium, shown here in yellow. Now, this diagram is from a couple of years ago. And so, of course, we know there's a bit of a blip in 2020-21 because of the coronavirus pandemic. But it's anticipated that rare earth demand is going to bounce back and continue to grow over the coming years. Now, one of the key points about the rare earth elements is that, of course, they don't occur as native metals in the Earth's crust. They occur in a wide range of ore minerals, and most of those ore minerals contain all the rare earths in varying quantities. So if you want to mine neodymium, you're also going to have to produce lanthanum and cerium, for example. And production is very much dominated by China. So let's take a look at the last 20 years or so of rare earth mining and research and some of the key events here. If we go back to 2000, rare earths were being produced in California at the Mountain Pass mine, and China was steadily growing production from its Bayan-Obo mine, where the rare earths are produced as a byproduct of iron oxide. And prices were fairly low and remained so until around 2010. And then China made a decision to tighten its export quotas. This may not have actually made that much difference in terms of the rare earths that were required worldwide, but it certainly made a difference in terms of prices. And it drove a really significant price spike, shown here in the red line, which is neodymium oxide price. Now, somewhat fortuitously, there was in fact another rare earth mine in development at that time, the Mount Weld mine in Australia, and in 2011 it opened. And that, as well as the fact that Chinese rare earths seemed to be supplying most of the demand that there was, led to much greater confidence and a rapid reduction again in prices. Indeed, by 2012, they were back down to where they had been really in late 2010, and they've bumped along at a pretty similar level ever since. It did lead to a reopening of Mountain Pass, which didn't last that long. It then closed again and more recently has started exporting again. What it did lead to was a great increase in research and development, and indeed in exploration. So no mines may have opened, but a lot of work has gone on, including the projects that I've been involved in. And we now know an awful lot more about rare earth element deposits than we did 10 years ago. Another key point is that in 2015, China began to tighten its environmental regulations. China had been considered as having some concerns around the environmental impact of rare earth mining, and since 2015, the Chinese government has been working very hard to improve the conditions of its rare earth mining. And any new mines that have opened have either been in China or have been very strongly associated with Chinese supply chains. So the Chinese control over rare earth supply chains very much continues to this day. So let's look at the geology and the types of primary rare earth element resources. You can divide rare earth element deposits really into two types. The high temperature deposits formed by magmatic and hydrothermal processes, and the low temperature deposits formed by erosion and weathering. And I've highlighted several different types there. I won't have time to discuss all of them today. So in terms of the high temperature deposits, we're going to focus on the alkaline igneous rocks and carbonatites. I won't talk further about vein and skarn deposits, although those are very important, particularly in Australia, where some great research has been done. And there's also the iron oxide apatite deposits, where you might well be able to produce rare earths as a byproduct of other mining. Again, I won't go into those in any more detail. Similarly, for the low temperature deposits, my focus will be on the laterites and iron adsorption clays. I won't talk about mineral sands, though they are an important source of rare earths. And I also won't go further into bauxites and phosphorites, although I will say now that the potential to produce rare earth elements as a byproduct of those major commodities, aluminium and phosphorus, is really important and an area of continued research. So let's start with alkaline rocks and carbonatites. And these are rather unusual and mineralogically complex igneous rocks, and they're often described as being rare. But that's really a misnomer, just as indeed the term rare is a misnomer for the rare earth elements. Alan Woolley from the Natural History Museum has been compiling data on all the alkaline rocks and carbonatites of the world throughout his career, and that's available as 4 books, but now also through the High-Tech Outcarb project you can see that data as a digital catalogue, and you can use the website shown there. This map shows the locations that have been identified by Alan's work. You can see alkaline igneous rocks in blue and carbonatites in red. And you can see that they really occur worldwide. They're not really rare. The two are commonly associated, with alkaline rocks perhaps being a bit more common than carbonatites. And a really important point is that they are most typically considered to be related to intracontinental rift zones. But in fact, that's not the only setting in which they're formed. This is a rather simple cartoon to demonstrate the tectonic setting in which you get alkaline rocks and carbonatites. And let's have a look at it in the context of the mineral system for rare earths in these types of igneous rocks. And there's been a lot of work done on this in the High-Tech Outcarb project by Graham Banks and others. So the first thing you need, of course, for that mineral system is a fertile source. Now, your alkaline rocks and carbonatites are typically considered to be mantle-derived, most commonly from enriched or metasomatized subcontinental lithospheric mantle, although mantle plumes represent another potential source. And that subcontinental lithospheric mantle is most commonly metasomatized either by fluids arising from subducting slabs and becoming trapped in the lithospheric mantle, or by more passive metasomatism around the craton margins. The next thing you need, of course, the next step in the mineral system is you need to cause partial melting of that mantle source, and you need to have a lithospheric pathway to move those magmas up into the crust. In intracontinental rift zones, of course, you typically have extension and you develop lithospheric scale structures that represent suitable pathways that can move those magmas up into the crust, where crustal processes such as trapping in magma chambers, fractional crystallization and magmatic evolution, and even potentially liquid immiscibility can operate to concentrate the rare earths. And finally, preservation is inevitably important. You have to have the right erosion level to have the deposit exposed at or near the surface. So all of that is quite well understood for intracontinental rift zones, and there is no doubt that you have magmatic complexes in these zones that are rich in the rare earths. But another setting that's perhaps not talked about so much is the postcollisional setting. For example, here where you've had perhaps an arc terrain collide and the development of an orogenic belt. And in that area, you've probably got very strongly enriched, really quite juicy or volatile rich subcontinental lithospheric mantle because you're relatively close to past subduction. And then within tens of millions of years of that collision, perhaps you start getting some orogenic collapse and development of major transtensional structures. And those can provide your lithospheric pathway for magmas to rise up into the crust and undergo the same crustal processes. But now in this setting, of course, we have very volatile rich magmas, and you need certain volatiles to represent ligands to transport the rare earth elements. So these settings can be very prospective for rare earth element deposits in alkaline rocks and carbonatites. So let's look at the importance of these post-collisional settings. And in these cases, we typically have alkaline rocks that are potassic to ultrapotassic because of their association with subduction zones. And we typically have a real association with carbonatites, which are often enriched in fluorine, in barium, appearing as barite, and the light rare earth elements. And the real type locality for this type of setting is the Mianning-Dichang belt of China, one of the world's great rare earth mining belts. But the Mountain Pass carbonatite in California is also associated with potassic alkaline igneous rocks, so it has post-collisional characteristics. And we've put together this kind of cartoon that shows the structure, if you like, of one of these post-collisional alkaline carbonatite systems. At depth, you'll have a magma chamber with alkaline magmas within it, which may have cumulates containing the rare earths in apatite, titanite, and allanite, for example. But often the rare earths will be concentrated because they're incompatible. They'll be concentrated in the magma, and you may come to a point where you have liquid immiscibility, generating carbonatite melts or carbothermal fluids. Your rare earths, particularly the light rare earths, will tend to go into those carbonatitic phases, and with them will be fluorine and other volatiles, and typically barium as well. And those will continue up into the shallower levels of the crust following existing pathways where they're in place and can form carbonatites or kind of carbothermal ore lenses. And generally it's those that contain the highest rare earth contents, and they are there at shallow levels. So we see these particularly where we have shallow levels of erosion exposed. So just looking at the potential in Europe and Africa, the EU Rare project looked at Europe's primary rare earth element deposits and resources and showed just how much potential Europe has. This map from a 2016 paper in Ore Geology Reviews shows you the range of potential rare earth belts across Europe. Some key localities, of course, the Gardar province in southern Greenland, where we have the Kvanefjäll project in the Ilamalsak complex. In southern Sweden, we have the Norra Kärr project, and over near Oslo, we have the Feng carbonatite, which has recently been studied in some detail by the Norwegian survey. And then if we want to look for post-collisional settings, then we have particularly the Tethyan belts in southern Europe, where we have localities like the Kiziljuren deposit in Turkey. None of these deposits for the rare earth elements have really developed beyond the exploration stage, with the slight exception of a small amount of production as a byproduct of mining for phosphate in the Kolar alkaline province in Russia. But really, otherwise, there hasn't been any significant development in Europe despite a huge amount of research and exploration. Let's step across to Africa. What about the situation in Africa? And here again, we know that there's a lot of alkaline rocks and carbonatites. They're focused around the craton margins. So if we look at this simplified map, you've got the cratons in pink. The pale blues and purples indicate Precambrian collisional belts around those cratons. And we've got Phanerozoic igneous rocks in red, including, of course, the major East African rift. And if I superimpose upon that alkaline rocks and carbonatites, with examples shown in yellow, and in pink, the rare earth deposits from the Harmer and Next paper in Episodes in 2016, you can see that around those craton margins, there's a lot of examples of rare earth element deposits. And in Africa, I should say, weathered deposits are also very important. Now, most of these known examples are of the intracontinental rift type, associated either with Proterozoic rifting of the Rodinia supercontinent or with the East African rift. But there are some post-collisional examples. And just like Europe, we have very little production of rare earth elements in Africa, despite the knowledge we have about the deposits. It's just small-scale production by rainbow rare earths at Gakara in Burundi. So what are the major challenges in developing mines in hard rock rare earth element deposits? Well, many of those challenges, of course, are economic, but there are also significant challenges around processing. Alkaline igneous rocks and carbonatites have very complex rare earth mineralogy and textures. The photographs here, which is from Anouk Borst's work, show at the top a nice clean eudialyte crystal from the Ilamalsak complex, And at the bottom, a more typical eudialyte crystal that has been replaced by a real complex intergrowth of different rare earth minerals. Because of this complexity, because of the range of minerals that will be present, each new hard rock deposit needs a completely new and unique beneficiation flow sheet. And we know that only some of those minerals are regularly commercially processed for rare earths, typically bastnäsite, monazite and xenotime. There's been a lot of research that has led to pilot stage processing for other minerals such as apatite, eudialyte, steenstruppine and allanite. Each of them have their own issues, and as yet there's not been commercial processing of most of these minerals. You also have potential for issues with radioactivity because some deposits will contain thorium or uranium in association with the rare earths. And even if you can develop a beneficiation process for your deposit and create mineral concentrates to extract and separate the rare earths from those mineral concentrates, you still need an offtake agreement with a major company, which is all too likely to be in China. So this is a major bottleneck for production of the rare earth elements in Europe and Africa. So what if some of that processing work had already been done for you by surface processes? A very large percentage of the world's rare earths come from either weathered deposits or placers and mineral sands. These deposits are low grade, but they can be very large. And typically, you've already had some separation of the minerals or some breakdown of the minerals. That means that processing may be easier than in the hard rock deposits. And so many of the new mining developments in recent years have focused on mineral sands and weathered deposits. The question that we asked ourselves in the SOS Rare project was, well, what happens when alkaline rocks and carbonatites are weathered? And so we started to look at the ion adsorption rare earth deposits. And these deposits are formed by weathering of bedrock in areas where that weathering is temperate to tropical. And you have breakdown of the minerals and release of the rare earths, such that they are adsorbed onto the surfaces of the clays in the soils. This type of deposit in southern China and Myanmar is the main source of the world's heavy rare earth elements. And because of the rare earths being adsorbed onto those clay surfaces, you can recover them by in situ or heap leaching, usually using chemicals such as ammonium sulfate. Now, we have no known examples in Europe of this type of deposit, but in Africa, there's the Tantalus deposit in Madagascar, and currently being explored the Makutu deposit in Uganda, and other examples in Malawi and elsewhere. So in the SOS Rare project, we decided to focus on the Tantalus deposit in Madagascar. And here, the really interesting thing is that you have alkaline igneous rocks that have been affected by tropical weathering. The photo shows what the deposit looks like. You just have the red soils of Madagascar, the lateritic soils. The upper part is the pedolith and the lower part, the weathered rock, is the saprolith. And we collected extensive borehole and pit samples. We characterised the bedrock geology and that of the weather profiles. We did elemental analysis and leaching experiments and even synchrotron X-ray absorption spectroscopy to investigate the structural position of the rare earths. And much of this work was led by Guillaume Estrade and Anouk Borst, and I've given a couple of references there, which I would urge you to look at for more detail. But the really key points here that aren't in this Tantalus deposit in Madagascar, the rare earths are adsorbed onto the clays in an identical way to those in China. But the controls on the rare earth content are really quite complex. They are in part associated with weathering processes. Different parts of the weathering profile have different contents of rare earths, but they are also controlled by the bedrock composition and the mineralogy. If you look at the chondrite normalized rare earth element plot there, then of course you've got light rare earths on the left, heavies on the right, and where you see the major anomalies in the lines, that is a europium negative anomaly. The black line shows you the rare earth pattern of the bedrock, and the blues, reds and browns show you the varying rare earth patterns in the weather profiles. You can see that the concentrations vary, but you can see that in general the pattern is mirroring that of the bedrock. So if the bedrock is light rare earth enriched, you're also going to see that the weathering profile, the ion adsorption deposit, is light rare earth enriched. In other words, it's not just a given that an iron adsorption deposit will be rich in heavy rare earth elements, and I think that's a really important point. Finally, just to mention weathered carbonatites, we haven't done a lot of work on these, but they really are a vital deposit type. Mount Weld is an example of a weathered carbonatite, as is Gakara in Burundi. And there's a section there through Nguala Hill from the Harmer Index paper in 2016. And essentially these deposit types will be light rare earth enriched. Again, of course, you're seeing the same compositions that you would see in the carbonatites, but may be very amenable to mining and processing. The difficulty can, of course, be finding them, as shown by this photo of geologists on the Eureka deposit in Namibia. So that leads me to my conclusions. And we can say that over the last 10 years, there's been a lot of research and exploration on rare earth deposits. We've learned a lot about their mineral systems. But what we haven't seen is the opening of many significant new mines outside of China. China very much dominates the supply chain for the rare earth elements. And most new mining, since Mount Weld opened, has been in mineral sands and iron adsorption type deposits. So in Europe and Africa, there's some excellent hard rock deposits, but it's challenging to obtain financing, and there's almost always a need for the processing steps to eventually move to China. So as geologists, of course, there's some challenges there that we can't perhaps address that easily, but we can provide the information to identify the best possible deposit types for future development. And we can think about innovative sources for the rare earth elements. And finally, I'd just like to leave you with the fact that we are working with the International Continental Drilling Programme to develop further research on understanding alkaline carbonatite complexes with a focus in Malawi. And please don't hesitate to contact me if you're interested in that.